When the security industry discusses large language models, the focus almost always defaults to the input. We build elaborate filters to catch prompt injection payloads and stop users from tricking the model. Catastrophic failures in modern LLM architecture happen when the model's own output is fed back into the core system. This is known as insecure output handling. It occurs the precise moment an application treats LLM-generated text, code, or structured data as inherently safe. Production models output structured JSON, SQL queries, UI components, and file paths. These outputs are sent directly downstream to database drivers, code interpreters, UI renderers, and core file systems. If those downstream systems execute or render these outputs without strict validation, the attack surface shifts. A single manipulated response turns the model itself into an authenticated proxy for remote code execution. Securing an AI application requires treating the model's output exactly like untrusted, malicious user input. Engineers have to rigorously map and enforce the exact trust boundaries of their architecture. Look at this execution pipeline map. Data flows from the LLM on the left, passes through a parser, and enters the execution environment on the right. That glowing line separating parsing and execution is the system's trust boundary. Under normal conditions, an agent might output a standard JSON payload to perform an action, like looking up an order. This payload includes expected parameters, like a legitimate webhook URL for notifications. Through an adversarial prompt, an attacker can force the LLM to inject a hidden, malicious URL into that exact JSON structure. The point of failure happens at the parser. The system accepts the properly formatted JSON and fires the webhook, but it fails to check if the target domain is allow listed. The trust boundary is breached. To identify these flaws without bringing down a production server, security researchers use non-destructive attacks. This methodology proves the vulnerability exists purely through observability, without mutating the system's core state. The most common version is a webhook beacon. The attacker uses the hidden URL injected into the JSON payload as a silent tracker. The engineer proves the exploit by monitoring their own external server logs. They wait to see if the target application sends an HTTP request to their unallow-listed domain. If that beacon fires, the proof is absolute. The output was trusted blindly by the parser, demonstrating a complete failure of the application's trust boundary. That pipeline map expands when we introduce an extraction layer between the generation and execution phases. This introduces a vulnerability called structured output extraction drift. It occurs when a system uses two completely different methods to pull code from text. Developers frequently rely on regular expressions to quickly scrape Python code blocks out of raw LLM output. Here, the LLM has generated a code block containing a hidden malicious instruction disguised as a comment. Regex is a pattern matcher. It aggressively strips out metadata, hidden strings, and comments that it deems unnecessary to the core code structure. Contrast that with an AST, abstract syntax tree parser. This parser evaluates the entire logical structure of the text, preserving everything, including the comments. The exploit happens in the gap between the two. If the security validator uses regex to check the output, it ignores the comment and marks the payload as safe. But the final execution environment processes the AST and runs the hidden instruction. The security check and the execution engine interpreted the exact same data differently. That mismatch creates an invisible, exploitable gap in the trust boundary. Trust boundaries break down even further in multi-agent orchestration, where systems chain multiple LLM actions together to complete complex tasks. The initial input handled by Agent A is usually heavily validated by the system's primary security rules. But during the handoff, Agent A's validated output drops directly into Agent B as unvalidated tool arguments. The system assumes that because Agent A is internal, its output is safe. Attackers exploit this unvalidated state using retrieval-augmented generation, or RAG, context poisoning. By injecting a malicious document into the retrieval database, the attacker can instruct the LLM to lower its own security settings, for example, forcing a command to include a flag like verify SSL equals false. When Agent A passes that data to Agent B, the application trusts the LLM's generated flag over its own hard-coded security policies. You prove this context poisoning by capturing the TLS handshake logs. The logs will explicitly show a successful external connection executed without SSL verification. Layering independent agents and RAG context multiplies the attack surface. It allows strict security schemas to be entirely bypassed while the data is in transit. Zooming in on the transmission line between the LLM and the orchestrator, we can observe the data streaming token by token. Developers stream tokens to drastically reduce latency, allowing the application to execute tool calls the moment the intended action becomes clear. But executing early means a destructive action can trigger purely on incomplete data chunks. The API fires the cancellation immediately. The backend processes the request before the user has even seen the first word of the response on their screen. This execution happens before the final closing bracket is received. That means it completely circumvents strict structural validation tools, like Pydantic, which require a complete JSON object to run. Checking a schema at the end of a data stream provides zero security if the application has already acted on the initial unvalidated chunks. We finally reach the deepest layer of the pipeline, the execution nodes, housing the SQL databases and Python interpreters. This is where we execute destructive attacks. Unlike observability beacons, these exploits trigger irreversible side effects, causing measurable state changes that survive system retries. In database orchestration, a primary vector is tool call double parsing. Here is a nested JSON string containing a discount value set to the string 0. Because of the architecture, this nested string gets parsed twice, first by the LLM orchestrator extracting the arguments, and then a second time by the SQL driver executing the query. Double parsing causes type coercion. The string 0 is dynamically coerced into an integer 0. This silently bypasses any string-based billing logic the application relies on. Engineers prove this destructive mutation by diffing the transaction logs and querying the database directly to expose the exact type mismatch. Over in the Python interpreter, attackers target module state corruption to achieve a sandbox escape. Many applications execute LLM output in seemingly restricted sandboxes. However, if the environment doesn't isolate module state between executions, the LLM can import and modify core host systems, like sys.modules. By overriding these core modules, the payload can silently corrupt query cache handlers or register destructive callback functions that trigger when the application shuts down. Destructive attacks prove that the model's output is being trusted completely beyond the reach of validation, leaving measurable terminal scars on the core system infrastructure. Securing this architecture requires treating every gap in the pipeline map as an open threat. Defensive layers must be rigidly integrated at every handoff point between generation and execution. At the extraction layer, you must enforce strict Pydantic schemas that fail closed. If the output contains unexpected fields or types, the system must reject it entirely, dropping the payload. At the execution layer, applications must use isolated, stateless sandboxes. Wiping the state between every single run is the only way to prevent module corruption. Across multi-agent handoffs, systems require HMAC or JWT cryptographic signatures. This ensures tool call arguments are explicitly verified before Agent B accepts them. LLM integration requires continuous telemetry and automated boundary probing across every execution path. The standard for modern engineering requires treating the LLM as a hostile external system. System security is not guaranteed by writing a clever prompt. It is strictly enforced by the cryptographic and structural barriers you build in the backend environment.